Hi guys, this is Dr. Gonzalez here, and this is going to be the last of a series of 3 videos that talked about how to run these analyses for the t-tests in depth. And I will also include one more video that will give you one more example of the 2-sample and the paired samples t-test, because I've had a lot of students in the past ask for multiple examples of how to do this by walking through Jamovi more than anything. So let's talk about the last one. Our last one is a paired samples t-test, which is going to correlate to a repeated measures design. So we are looking at 2 measurements that could be from the same individual, object, or related unit. So some examples of paired things could include a measurement that is taken at 2 points in time. So say I have a pre-test, I give the intervention, and then I do a post-test. So I took 2 points in time. I could also take a measurement under 2 conditions, right? So I complete a test under a control condition, and then with the same participants, I complete a test under an experimental condition. Or you can also do measurements that are taken from 2 halves or sides of a subject or experimental unit. And this is kind of an odd thing to conceptualize, but imagine you were looking at reaction time on pushing a button with right hand versus left hand. So you have your participant there and you tell them, say, whenever the word trauma appears on the screen, you have a list of words, right? And whenever trauma happens, you're supposed to push a button with your right hand, and whenever something like stress, you see that word, you have to push something with your left hand. So you're comparing reaction times between right and left hands. And I know trauma and stress are 2 weird things there, have nothing to do with this. It was the first thing that popped into my mind, guys. But the purpose of that paired samples t-test is to figure out if there is evidence to prove that the mean difference between those paired observations was significantly different from 0, okay? Paired samples t-test is an example of a parametric test. So you'll also hear that paired samples t-test referred to as a dependent t-test, a paired t-test, paired samples t-test, or repeated measures. And the variable that you use in this test is a dependent variable and a test variable that are continuous, and they're measured at 2 different times or 2 related conditions or units, like we had talked about earlier, like treatment and then a control condition. And then my little graph that I have, or my little image over here, I just had some subjects, right? I've got subjects right here. Those subjects take a pre-test, they do some sort of intervention, then they take a post-test, and they take the test right there, and then I'm looking to see if there's a difference between those scores. And I'm looking at it across all these subjects here. All right, so when do we use this? Again, paired samples t-test, we want to test 2 points in time, pre-test, post-test, 2 different conditions with the same subjects, 2 measurements, or a matched pair. So what do your data need to look like? Your data need to be a continuous dependent variable. That means it's measured as an interval or a ratio, and you're going to record it in 2 separate variables. And then you also have related samples. These are dependent observations. You'll notice in the previous example, the 2-sample, we were very, very interested in having independent observations. Now we want them to be dependent. So the subjects in each sample or group are going to be the same. So the subjects that are in group 1 are also in group 2. You had random sampling of your data from the population. You've got an approximately normal distribution of the differences between the paired values, and you don't have any outliers. Our hypotheses can be expressed in 2 ways. You can either say it through equal means or difference between means. So these are all 2-tailed examples. So our H sub 0, or our null, is mu1 is equal to mu2. Our alternative is mu1 is not equal to mu2. And then this one down here is just telling me about the difference, right? So for our null, the difference is equal to 0. There is no difference. And then alternative is that mu1 minus mu2 is not equal to 0, and that means that there was a difference. Here is our formula. So our formula looks a little bit different. This one looks a whole lot more simple than the other ones we looked at, but it's your T is equal to X bar difference, which is the sample mean of the differences, minus 0 divided by your estimated standard error of the mean, so S sub X bar. And that is true where your S sub X bar is calculated as the S difference, which is the difference in the sample standard deviation divided by the square root of N. N is your sample size, which is the number of observations. All right, so how do your data need to be set up? They need to be set up a little bit differently than they were in the previous examples. So your data is going to have two continuous numeric values. They're going to be represented in columns in your analysis. The two variables are going to represent a paired set of variables for that subject. That's a row. And if your data are arranged any differently, it's going to require you to restructure it in order to reflect that format. So in your data set, I have included data for you to do this with me in Jamovi. And here is our scenario. This one is about sleep deprivation. So sleep deprivation is a construct that when we observe it in an experiment, we have to be extra careful because it's manipulating a biological function that is important to everyone. So in order to reduce the number of participants in a study, which is a way that we lower risk, we might use the same participants in two conditions. So we bring in one group of participants, we have them go through one of our treatment conditions, and then they come back at another point in time and go through another treatment condition or a control condition, or vice versa. So that's repeated measures in design, and that requires less participants, therefore lowering risk. So this is a totally made up scenario here, but for this scenario, our pretend research question is, does one night of sleep deprivation affect daytime sleepiness measured with the Karolinska Sleepiness Scale compared to a normal night of sleep? So what I have is a group of participants coming in, and they're going to come in and sleep a normal night, and the next morning they're going to wake up, and we're going to give them the Karolinska Sleepiness Scale and record how sleepy they feel that next day. Then we're going to have them come in again, and we're going to have them stay up all night. We're going to deprive them of sleep for that night. And then the next morning, we're going to also give them again the Karolinska Sleepiness Scale. And then we're going to compare those scales to see if they reported being more sleepy after being sleep deprived, which is what I would think, right? If you stayed up all night, the next morning you would probably say you were sleepier than you were if you didn't stay up. So here's our research question again. Does one night of sleep deprivation affect daytime sleepiness compared to a normal night of sleep? Your independent variable is the sleep condition. It's either normal or sleep deprived. And then your DV is sleepiness. And we're going to measure that with a measurement tool that exists called the Karolinska Sleepiness Scale, or the KSS. So one night, they're going to tell me how sleepy they feel the next day. Won't let them sleep the next time they come in. They stay up all night. And then I'm going to ask them their KSS the next day. So just a little bit of information so you can understand where I'm going conceptually with this. The KSS is a very brief self-reported measure about how sleepy you feel at that moment in time. So participants rate how sleepy or alert they are using a scale of 1 to 9. So it's looking at sleepiness. So the lower the score is, the more alert the person is. And the contrary to that is that the higher a score is, the greater sleepiness they're reporting. So it's 1 is extremely alert all the way to 9, which is extremely sleepy or fighting sleep. So in this particular research design, each participant is going to come in and do a normal night of sleep, and then another night they're going to come in and do sleep deprivation. They're going to take the KSS twice after each of those nights. So we're going to have 2 scores for each participant. And what we're going to look at is across all of our participants, if that mean sleep deprivation score is higher, the participants are going to be sleepier. Okay. And And the KSS is really cool because it measures current sleepiness, not their long-term habits, not their sleep duration. It's how sleepy did you feel at this particular moment. And that moment is directly after their night. So we're going to do a two-tailed hypothesis just because, right? I just wanted to do two-tailed. So our null is that there's no difference in the KSS sleep scores after a normal night of sleep or after one night of sleep deprivation. We could also write that in terms of mu. We would say mu of normal sleep equals mu of sleep deprivation. Our alternative would say that there is a difference in KSS scores after a normal night of sleep and after one night of sleep deprivation. We can write that in terms of mu by saying mu normal sleep is not equal to the mu of sleep deprivation. So we're going to recruit 101 participants. The reason why I did that was so you could have an easy bounding criteria using the chart. Each participant's going to give me 2 KSS scores. We're going to have a KSS score after a normal night of sleep and a KSS score after 24 hours of sleep deprivation. So let's use our chart and figure out our alpha and critical levels. So we just said on the previous slide here that we've got 101 participants. So n minus 1 gives me 100 for our degrees of freedom. And we said that this was going to be two-tailed at a 0.05 level. So if I follow 100 participants and a t.975 in two tails, 0.05 right there, my critical value is 1.984. So the region under the curve bounded by our criticals is going to be between positive and negative 1.984. So here's what that looks like, right? I've got my t-distribution. It's a two-tailed test. Alpha is 0.05 with degrees of freedom of 100. My corresponding critical values are plus or minus 1.984. There's my negative 1.984. There's my positive 1.984. So I'm going to reject the null if my score, if my difference in my means falls in one of these two critical regions. If it falls in the non-critical region, I'm going to fail to reject, and I'm going to say that there was no significant difference between the two conditions. So let's run this in Jamovi. First thing you need to do is go to Analyses, T-Tests, and go to Paired Sample this time. So we're going to go back over here to Data, go to Analyses, T-Tests, Paired Samples. And what we're going to do is we're going to move our paired values over. So you're going to move your variables of KSS normal sleep and KSS sleep deprivation. So KSS normal sleep and KSS sleep deprivation. And if you went over here and looked at the data, you would see that this time the data, there's an ID that stands for each participant, and there's 2 scores for each participant. So there's the KSS for participant number 1. There's the KSS after a normal night of sleep. This participant reported a 3 on the KSS scale. And then after their night of sleep deprivation, they reported a 6. Go back to my paired samples t-test. Sorry, it moved it all over for me. Now let's see what else we want to choose for our options here. We want to make sure that we're under a student's test. Our hypothesis is that measure 1 does not equal measure 2, and we want to make sure we have the mean difference, effect size, and descriptives. So we're going to go over to Jamovi, and we're going to make sure that we have measure 1 is not equal to measure 2. Don't worry about missing values because there's nothing missing. We're going to click the mean difference, the effect size, and our descriptives. Okay, now we could do an assumption check of normality. Okay, it's a different test this time. For a paired sample situation, it's actually the Shapiro-Willick. But we're not going to worry about that because actually I think if we did that, P is less than 0.001. Actually, there is a violation of normality, but we're not going to go about that right now because that makes things really complicated. We're going to keep going with what we've got here. So here are the results that we got. The mean for normal sleep was 3.15, and the mean for sleep deprivation was a 6.40. And I actually need to fix this because it says hours, and there's not hours this time. It was at 3.15 on the KSS. So mean for normal sleep, their mean score for that normal night on the KSS was 3.15. Remember, I told you the lower the score on the KSS, the more alert they were. And the mean for sleep deprivation is 6.40. The higher that KSS score, the sleepier the person reported being. So the mean difference between their KSS scores was 3.25 points. Down here, I've got my student's T statistic, negative 35.4 with 100 degrees of freedom. P is less than 0.001. There's our mean difference in score. And there's our Cohen's D, which is a significantly large size difference. Then down here, we have all the descriptives we need to write this up. So remember, higher score, sleepier the person reported being. So our critical value was plus or minus 1.984. We would reject if T is less than negative 1.984 or greater than 1.984 positive. That's at the 0.05 level. And then we would fail to reject if it fell anywhere in between the two critical regions. Here's our statistic. It's negative 35.4 with 100 degrees of freedom, and that is significant at the P is equal to 0.05 level because P is less than 0.001. So what are we going to do? We're going to reject our null. The statistic was negative 35.4. That is way over to the left past 1.984. So we reject our null. There was a significant difference in scores on the KSS after 24 hours of sleep deprivation. And our effect size was extremely large. Our Cohen's D was negative 3.53, meaning that the average change from normal sleep to deprivation was about 3.53 standard deviations. So you can write this up. You would say participants had significantly higher sleepiness scores after one night of sleep deprivation with a mean of 6.4 and a standard deviation of 1.21 than after a normal night of sleep with a mean of normal at 3.15 and a standard deviation of 0.89. Then you report your statistic. T of 100 degrees of freedom is equal to negative 35.4, comma, P is less than 0.01, and Cohen's D is equal to negative 3.53. So a sentence just summarizing this would be, this indicates that sleep deprivation significantly increased self-reported sleepiness on the KSS. So that is the end of our in-depth look at the 3 different types of t-tests that we reviewed. I'm going to include one more video where I'm going to walk you through again a database where a data set where you can look at these particular tests. I'm only going to do in that intensive video a 2 sample and a paired sample because the 1 sample we've already done, and I just had a request for some more examples that walk through Jamovi. So I hope you've enjoyed these and have learned a lot. Take care.